Hello, we are here to discuss intermolecular forces. Um, where intermolecular forces fit into what we're talking about right now are probably a subcategory of uh, covalent molecular compounds. So we started with ionic compounds, talked about covalent molecular, looked at geometry of those bond angles, and now that's going to play into how we're going to think about intermolecular forces. So we probably just need to start with talking about what these are. The name does explain a fair bit of it, but intermolecular forces are forces that exist between molecules. And the reason that they're so important is when it comes right down to it, the attraction between two different molecules of a compound um, really impact how they behave in a macro sense. When we're talking about some of the physical properties, whether it's melting point or boiling point, those are things that we refer to in terms of volatility. The more volatile a compound is, the more readily it changes state into a gas. So when we think about intermolecular forces, it's just as simple as how much do these two molecules, okay, whatever we're looking at, attract to one another. And if they're really sticky, if they are attracted to one another and stick together, then they have low volatility. Whereas if there's little to no intermolecular attraction, they would have high volatility. They're very likely to break into the gaseous state of matter. We're going to cover three types of these. Um, and starting at the bottom, going down, or starting at the top of this list going down, the top one is actually the weakest of the three, van der Waals forces. We'll then go to dipole-dipole attraction and close it out with hydrogen bonding, which is definitely the strongest of these three intermolecular forces. We'll probably end up needing to take the longest amount of time talking about van der Waals forces because we're really going to have to break down a few concepts that will help us approach all of these. We'll lay some groundwork with van der Waals, and then it will, I think, help us understand what's going on for the next two when we talk about dipole-dipole and hydrogen bonding. So a little bit of language in this first bullet point that I think we're going to need to talk about. Nonpolar molecules have no permanent dipole movement. And we're going to have an example that will help us take a look at this in just a moment. But figuring out if a molecule is polar involves looking at really two features. First, we need to look at the electronegativity differences between bonding atoms. So electronegativity is the ability of an atom to attract a bonding pair of electrons. And elements that are more electronegative than other elements do just that. They pull the bonding pair of electrons closer to the electronegative element. All right. The second factor is the molecular shape. So when we think about molecular geometry, some shapes simply don't allow for a polar molecule to exist. And you're going to see again in just a moment what I mean by a polar molecule, but the very simple, straightforward version is when there's a polar molecule, there's an imbalance in charge on that molecule. So there'll be a higher concentration of negative charge on one end, and then a higher concentration of positive charge on the other end. And it's not a full +1, -1 situation. It's a partial positive and partial negative. So stick with me on this as we get into examples. I think that will become a little bit more clear. Electrons, even when they're involved in a bonding situation, are always moving, right? And if you think of just an atom, the location of the electrons is constantly changing. And what that means is the density of electrons in a given area is always changing as well. And that's simply due to random chance, right? If electrons are moving very fast in a random fashion, there will be times when there's a higher concentration of electrons in a given area. Because of this, there will be what's called a temporary or instantaneous dipole. So the idea here is, since electrons are constantly moving about within a molecule or an atom, at various times, there will be a majority of the electrons in one area in this molecule, just because of random chance, just because of how they're distributed while moving around. And because there is a higher concentration of negative charge in this one area, that must mean that the other portion of this molecule has a lower concentration of electrons than average. When this molecule that has a temporary or instantaneous dipole is then next to another molecule, okay, it causes an effect that is generally referred to as an induced dipole, right? So the molecule that has the instantaneous dipole is a little bit more negative over here and a little bit more positive over here. Since it's a little bit more negative over here, when it's next to a different molecule, it will actually push those other electrons in that other molecule away. And that causes it to have an imbalance or a temporary dipole. But the positive end of that second molecule is going to be close to the negative end of the original molecule. And there's an attraction there. That attraction is the van der Waals force. So we can look at chlorine as a nice example here. Chlorine is a halogen, so it's diatomic. So we can see that on average, the electron cloud for a chlorine molecule is evenly distributed, right? There's not a higher concentration of electrons anywhere. This over time is true. Over the long run is true. However, at any given moment, because those electrons move randomly, we will end up with a situation where there's a higher concentration in one end than the other just because of chance. So if you look at the central molecule on this slide, you can see that there's a partial positive charge on the left side and a partial negative charge on the right side. And the coloration in the molecule is actually indicating this as well. Where there's a darker pink, there's a higher concentration of electrons. So this central molecule has this temporary dipole, this instantaneous dipole, and it happens simply due to random electron movement. However, because it's next to another molecule of Cl2, what we notice is that this partially negative charge on the right-hand side of the molecule will cause the electrons in the molecule next to it to move to the other side, right? Opposite or like charges repel. So the partially negative charge in our central molecule pushes the electrons in our right-hand molecule to the right side. But now we have a partial negative and a partial positive. And you can see the arrows just below those two molecules. That attraction, the partial negative and the partial positive, is a van der Waals force. Okay? They happen quickly because it's temporary and then induces this movement in the molecule next to it. It doesn't last for very long. Okay? It's temporary, it's there, and then it's gone. This is maybe a nice chance to point out that chlorine, you can see from this molecule on the left-hand side, is generally a nonpolar molecule, right? Because there's no permanent polarity. There's no permanent difference in the distribution of electrons. So we can look at some examples of this in just a moment, but here are the takeaways. These temporary dipoles create an attraction between molecules. Again, intermolecular forces are between molecules. And like I stated previously, van der Waals are the weakest of these intermolecular forces. We're going to learn about dipole-dipole and hydrogen bonding, and those subsequent intermolecular forces will increase in strength. For looking at the strength of van der Waals within molecules that only have this intermolecular force, the key is the number of electrons. And we can kind of make a shortcut for that, the size of the molecules. So molecules that are larger or have more electrons are going to have higher van der Waals forces. And the reason for that is they can just create a larger differential in charge. It's like having more people on a boat, right? If you have one person on a boat and they lean to the side, there might not be that much of a difference. But if you have 15 people on a boat and they all go to one side, it's going to create a big problem, right? And so the more electrons that are in a molecule, the greater the differential can be from the partial negative to the partial positive. If van der Waals are the only intermolecular forces present in a molecule, those molecules are generally going to have pretty low melting and boiling points because it is a relatively weak intermolecular force. I do want to point out that every molecule has van der Waals forces, right? Because all it requires is a molecule having electrons, which they all do. So here's a selection of the halogens, starting with fluorine, going down through iodine. What I just want to start by looking at is the state of matter at room temperature. Both fluorine and chlorine are a gas at room temperature. That means they have a pretty low boiling point and melting point. Okay? Bromine is a liquid at room temperature, so still a low melting point, but its boiling point is getting a little bit higher. And iodine is a solid, which means it actually has a higher boiling and melting point. And you can see how boiling point is changing here. The middle column, one of the two middle columns, has the boiling point information in degrees Celsius. Mr stands for relative mass of the molecule. Really, that's a nice stand-in for the size of the molecule. The mass increases as you move down the chart here. Really what that's standing in for is an increased number of electrons. So as the number of electrons increases here, our van der Waals forces are increasing. Okay, so the intermolecular forces are larger in iodine than they are in fluorine. And the way that that manifests itself in the physical world, the thing that we can actually observe with regards to this is the boiling point, right? Is the state of matter at room temperature. So we can see that these molecules, the way I like to describe it, is they get stickier. They cling together more as they get larger because of increased van der Waals forces. Here's another chart with a very similar concept. This is a homologous family. In organic chemistry, we refer to these as alkanes. So you have methane, ethane, propane, and butane. Again, they only consist of bonds between carbon and hydrogen, and then some bonds between carbons. So they're all, relatively speaking, non-polar bonds. The difference in electronegativity is very small. So van der Waals are the only intermolecular force present in these molecules. So as the size of the molecule increases, there are more electrons. More electrons mean they can create a bigger charge differential with their momentary or induced dipole. And we see boiling point increasing as we move through those. Dipole-dipole is the second class of intermolecular force that we need to talk about. And there are actually some very significant similarities in dipole-dipole as van der Waals. However, there are some significant differences as well. When we talk about dipole-dipole, it always involves molecules with a permanent separation of charge. It's often what we refer to as polar molecules. So for a molecule to have a permanent separation of charge, like we said previously, two things need to be true. There needs to be a significant difference in electronegativity for two atoms that are bound together, and the shape of the molecule must allow for this permanent distribution of charge. And what we'll find, and we'll have an example of this in just a moment for you to visually look at, is that the molecule will have a permanent partial positive and a partial negative, as will its neighbors if they have the same identity. And that permanent partial positive will be attracted to a permanent partial negative on a neighboring molecule. Because this distribution in charge is permanent in these molecules, that attraction is always going to be there. Unlike van der Waals, where that attraction is only there some of the time, this is permanent, which means it's going to be stronger. And what we call that attraction is a dipole-dipole attraction, right? Dipole meaning two poles, positive and negative. Every molecule in a sample of this, right, is going to have a partial positive and a partial negative. They'll attract, and that is our second intermolecular force. The strength of this is based on bond polarity. What we mean by bond polarity is the difference in electronegativity of the atoms involved in that bond. So in this example that we're looking at visually, we have hydrogen and chlorine. Chlorine is significantly more electronegative than hydrogen, okay? So in that bond, it just does a really good job of attracting the bonding electrons, okay? That creates this permanent dipole distribution, okay? The chlorine virtually always has more electrons around it than the hydrogen does. So this is a permanent partial negative and a permanent partial positive. Like I mentioned on the previous slide, since these dipoles are permanent rather than instantaneous or momentary, okay, this attraction is always stronger than van der Waals. So you can see this arrow attracting the hydrogen side of one molecule and the chlorine side of the other molecule. That is a dipole-dipole attraction. And finally, hydrogen bonding. This one won't take as long as van der Waals, I don't think, but will take probably just a touch longer than the permanent dipole or dipole-dipole attraction. Hydrogen bonding is undoubtedly the strongest intermolecular force. And I want to be clear here. It is the strongest intermolecular force, though it is not as strong as an ionic or covalent bond. Right? This is an attraction between molecules. It's not a chemical bond. So hydrogen bonding only appears when hydrogen is bound directly to an extremely electronegative atom. There's actually a nice shortcut that we can use to think about this. Um, Really, what you need to watch for is when hydrogen is directly connected to either fluorine, nitrogen, or oxygen, right? It has to be connected directly to one of those three types of atoms for a hydrogen bond to be possible. Hydrogen bonding is really just a specific named example of a dipole-dipole bond. But the effect is so strong, we set it apart as its own category. When hydrogen connects to either nitrogen, oxygen, or fluorine, those three atoms are so electronegative that they almost completely take the electrons. Okay, they almost totally just control the bonding electrons in this case. And that means the only thing that's left of the hydrogen atom at that point is a proton on the end of a covalent bond, right? Except the covalent bonding electrons are mostly around either the nitrogen, oxygen, or fluorine atom. There's just this random single proton sticking out the side of a molecule. The attraction that we have named as a hydrogen bond is actually that proton making a connection with a non-bonding electron pair on a different atom. And again, this is not a covalent bond. It's not an ionic bond, but it's a dipole-dipole attraction that's just unique enough for us to call a hydrogen bond. This effect is really prevalent in water. So we have a couple of water molecules here that allow us to take a look at this. Okay. Around the oxygen, you've all drawn a Lewis dot structure for water before. But you see there are two lines representing covalent bonds to hydrogen atoms. And then there are two non-bonding electron pairs on the oxygen as well. Okay, the molecule has a bent shape, 105 or so degrees for the bond angle. What I want you to notice is this bottom central water molecule, right? The covalent bonds within this molecule are so polar, the electronegativity is so great that the oxygen has almost totally taken control of the bonding electrons. And where you would see the hydrogen atom here, that's almost like a little just single proton sticking out the end of the molecule. Well, that proton has a positive charge, and it is going to attract this non-bonding electron pair on a different water molecule, right? And this effect is really incredible. As I've referred to it as a couple of times already in this talk, it makes molecules especially sticky, right? This causes molecules to really attract to one another. And they actually are much less likely to change state from a liquid to a gas in this case. This chart can be a little confusing to look at, but we'll talk through it. So there are period 2 elements that are bound to hydrogen, and then period 3 elements bound to hydrogen, period 4 elements bound to hydrogen, and period 5 elements bound to hydrogen. And this is specifically for groups 4, 5, 6, and 7, so the vertical columns on the periodic table. What you'll notice for most of this chart is that as molecules increase in size, their boiling points increase. And that's exactly what we would expect to see because of van der Waals, right? That as molecules increase in size, their boiling points also increase because of van der Waals, the first intermolecular force that we looked at. However, there are 3 significant outliers. There are 3 pretty darn small molecules that actually have quite high boiling points for their size. It's H2O, HF, and NH3. And in each of these cases, we see that hydrogen is connected directly to one of the three extremely electronegative elements that I talked about previously: oxygen, fluorine, or nitrogen. So H2O, HF, and NH3 are all going to have hydrogen bonding present in them, right? And this leads them to have high boiling points for their size. A couple more examples here. Methoxymethane is an organic molecule where there's an oxygen that makes a bond to two carbons, and then each of those carbons makes a bond to three hydrogen. Okay? So the oxygen is connected to the carbons in this case, and not the hydrogens. On the right-hand side, it's ethanol. And it has a slightly different shape, though it's made up of the exact same elements. However, in the case of ethanol, there's a hydrogen bound directly to an oxygen. So even though they are made up of the exact same atoms, but in a different arrangement, that means they have the same number of electrons. The methoxymethane has a boiling point of negative 23 degrees Celsius, while ethanol has a boiling point of 79 degrees Celsius. That's almost 100 degrees difference, right? So simply by the fact that there are hydrogen bonds present in ethanol, it increases the boiling point significantly. Another way we could say that is it lowers the volatility significantly. So water, as I mentioned, is kind of a classic example. All right. In its solid state, it can form up to 4 hydrogen bonds. Liquid usually only makes 2. And what's neat about that is it causes solid water to have a tetrahedral arrangement. And solid water is less dense than liquid water because of this. So next time you put ice in water, just look in your cup, right? The reason why ice is less dense than liquid water is because of the hydrogen bonding present in this tetrahedral arrangement. And you can see the hydrogen bonds in this image by the little dashed lines connecting different molecules here. Finally, and this is just kind of a little peripheral information, hydrogen can appear within a couple of different types of large molecules. They're really important in biochemistry when we look at the structure of proteins or DNA. And then I really want to emphasize, yes, hydrogen bonding is the strongest intermolecular force, but it is still an intermolecular force, okay? It is 10 to 15 times weaker than covalent or ionic bonds. So those are the 3 intermolecular forces that we need to be familiar with.